In this lecture, we are going to bridge the gap between exponential smoothing and the Holt-Winters model. This is going to be done in a series of steps, and the first step is to understand exponential smoothing from a different perspective. That is, from the perspective of time series forecasting. Previously, our perspective was simply, what are different ways that we can take the average in a time series? Now it's more about, how do we fit a model to the time series, and then how do we use that model to forecast future values? Mathematically, this is the same as before, but philosophically, it's different. To do this, we're going to have to introduce some new and more precise notation. Let's begin by reviewing the exponentially weighted moving average once again, but using our new notation. So now we have y hat at time t is equal to alpha times y of t plus 1 minus alpha times y hat at time t minus 1. In this form, y hat at time t is our exponentially smooth version of y at time t. Y of t is the value from our time series at time t. Alpha is again the smoothing parameter. The next step is to now phrase this as a forecasting model. In this form, the equation looks as follows. You'll notice that I've introduced this vertical bar symbol, which, as you know in probability, means given. So on the left-hand side, we're saying y hat is the exponentially smoothed forecast for time t plus 1 given the known values at time t. On the right-hand side, we have alpha times y of t as usual, plus 1 minus alpha times the previous exponentially smoothed value. Notice something interesting about this. The time indices have changed. For the current equation, the y hat on the left is for the time index t plus 1. The y hat on the right has the time index t. If you look at the previous slide, the time index t is on the left and t minus 1 is on the right. This is probably extremely confusing at this point, and I wouldn't blame you for thinking so. It will make much more sense when we look at the code and you actually observe this behavior for yourself. Now, realize that I didn't invent this. This is all part of the Holt-Winters model, so don't blame me if you find it confusing. By the time we reach the full Holt-Winters model and you see it in action, you will see that this all makes sense. Again, recognize that this is now a forecast. Previously, we were not forecasting, we were just calculating averages. The forecast for the next time step is equal to alpha times the currently observed value plus 1 minus alpha times the current exponentially smoothed fitted value. The next step is to express the simple exponential smoothing model in what is called component form. This will make it seem like overkill at this point because there is only a single component. However, the Holt-Winters model contains multiple components, which is where this becomes useful. So in this form, the forecast equation looks as follows. We say that y hat at time t plus h given t is equal to L of t. That is, the forecast at an arbitrary h steps ahead is equal to L of t, whatever that is. Then, the smoothing equation says this. L of t is just the exponentially smoothed average of y of t, the time series. Notice that L of t now becomes the exponentially smoothed average, and y hat becomes the forecast. Also note that L of t gets back its original time indices from the previous lecture. That is, we now have t on the left and t minus 1 on the right. So L of t is itself not a forecast, but the forecast is based on L of t. For this simple model, the forecast is simply assigned to be L of t, but this will get more complex in later lectures. So what does L of t represent? L of t is called the level, which will become more clear when we put it into context later on. Basically, level can be thought of as the moving average, which kind of makes sense. The level is the average value of the signal in time, but the actual signal may fluctuate around that average level. One important thing to note about this forecasting model is that it's not very expressive. The forecast is simply a constant value. It's always L of t, no matter how many steps ahead you want to forecast. This must be the case because remember, the exponentially weighted moving average is nothing but an estimate of the mean. Since all we're estimating is the mean, then that's the only thing we can predict. After we've stopped collecting data, we have no idea how this mean will change beyond the last known data point, and so our forecast simply consists of predicting the same mean value for each time step. The last thing we're going to do in this lecture is talk about how this will work in code. Previously, we looked at pandas as a way to calculate the exponentially weighted moving average, and we've noted that this lecture didn't introduce any new concepts other than some renaming of variables. However, in the next coding lecture, we're going to use stats models to perform exponential smoothing, which has a model that works more in line with what we discussed in this lecture. Furthermore, it's capable of making forecasts, so that will allow us to use exponential smoothing as a predictive model, rather than just some way of taking the average. So how does it work? Since this is the first model from stats models we'll be looking at in this course, how it works might be surprising if you come from a scikit-learn background. Basically, remember that this is a different library, so it has a different API. First, we start by importing the class SimpleExpSmoothing from the whole Winters module inside stats models. Next, we create a model by instantiating an object of type SimpleExpSmoothing. Note that when doing this, we pass in the dataset, which should be a univariate time series. Unlike scikit-learn, which expects a two-dimensional array as input, this model expects a one-dimensional array because the only dimension is time. In scikit-learn, it's number of samples by number of features. Also notice that, unlike scikit-learn, where the data is passed into the fit function, with stats models, the data is passed into the constructor. The stats models object does have a fit function, which is what we will call next. This function accepts some parameters, such as alpha. So it's kind of like the reverse of scikit-learn. In scikit-learn, the constructor usually takes in the hyperparameters, and the fit function takes in the data. In stats models, the constructor takes in the data, and the fit function takes in the hyperparameters. For us, we're going to pass in alpha into the fit function, in addition to setting the argument optimized equal to false. Note that for all of the models in the whole Winters module, it's possible to fit parameters to the data. This makes it more like machine learning than simply calculating a moving average, but this will make more sense as our model gets more and more complex in later lectures. In order to make what we're doing equivalent to what we did previously, we will not try to optimize the value of alpha. Basically, alpha would be optimized in order to minimize the error on the training set. If you're familiar with machine learning, then you will understand that this involves taking the mean squared error between the true time series and the predicted values, and then minimizing that with respect to alpha. If you're not comfortable with this idea, it's not necessary to know, so don't worry about it since we're not going to use it anyway. Alright, so the fit function returns a result object, which is again different from what you're probably familiar with from scikit-learn. In scikit-learn, you just get a reference to the model object itself. In stats models, we get a result object. Specifically, we get back a whole Winters results object, so you can look up the documentation if you're interested in seeing what functions can be called on this object. The first function we are interested in is the predict function. The way it works is this. You pass in a start date for the start argument and an end date for the end argument, and then this will return an array containing a prediction of time series values for those dates. Note that these dates can be in sample or out of sample, meaning that they can be dates from the training set or after the training set. If the predicted dates are from inside the range of the train set, we call that an in-sample prediction. If the prediction dates are from outside the range of the train set, we call that an out-of-sample forecast. A simpler way to get predictions is this. If you want all of the train predictions, you simply call the attribute fitted values. This way, you can avoid having to figure out the dates that you need for the start and end arguments. A simpler way to get a forecast is to simply call the forecast function. This accepts as input the number of forecasting steps. So for example, if you want to forecast 10 steps ahead, you just pass in 10. There's no need to figure out what the date is 10 steps ahead. Passing in the integer 10 is enough. Note that this assumes that your forecast begins at the time step after the end of the train set. So if your train set goes from 1 up to big T, then your first forecast prediction will be for the time index big T plus 1.